15 seconds is a long time when you're waiting for them to pass. Yeah. You can hardly even cook microwave popcorn in 15 seconds.
Yeah. Oh, we got feedback. We have feedback.
Oh, that's because of my YouTube. Let me just turn this down to 0 and that'll fix that. All right. I think we should be alive and kicking. Hello, everyone. Welcome to Sidewalk Science. This is where we talk about the intersection of science
And sidewalks.
and sidewalks. We're humanists. We're supported by the American Humanist Association and the local Prairie State Humanists in the Chicago area. And as humanists, we maintain that the only way to know what's real and true and possible in the world is through scientific study. That's not to say things like emotion and art and literature are not real, even though those are not necessarily scientific pursuits, but those are constructs of the wonderful human imagination. Yeah. We also think that religion is a construct of human imagination.
Mush.
Yeah.
I'm going to put a shout out to philosophy. I'm not going to discount philosophy in favor of science.
No, but that's what science started.
That's right. That's right.
Mom and dad.
Thank you, Ivan. And I agree with Ivan. I just overlooked that. But philosophy, sort of the foundational metaphysics. Our metaphysics is grounded on, kind of an empiricism that the natural world is something we can learn about by watching it.
Yeah. Empiricism is really all we have.
All right. So welcome to Sidewalk Science. Our regular guest panelist, Abby Hafer, is not available today. She's recovering from a second vaccine. She says she's feeling a little under the weather. It's sad. We're going to miss her. But today we have a physics topic, and we have several physicists in the room with us here. Yeah. So we should be pretty well covered. Well, you're kind of like the rest of us. You're well versed in almost everything.
I'm a chemist.
Yeah.
I take, once the physics is done, I do the chemistry.
Yeah.
But no.
So we've got
complicated stuff, the stuff with a billion atoms in a big molecule, stuff like that, right?
Right.
That's what we do. We don't deal with muons. So they're just, huh?
Yeah, look at how long it took physicists to figure out the hydrogen atom. I mean, much less anything else, right?
Whereas we went, it's water.
So, welcome. Thanks for joining us. I think all of us now have gotten at least one vaccine shot. I hope those of you watching either real time or watching subsequently have also been able to find a place to get vaccinated. We very much encourage you to do so. It's the right thing to do, and it's justified by all kinds of science. So that's what we've been up to. Joanne, you been up to anything else?
When can we now get back on the sidewalk if we've been vaccinated and real?
Oh yeah.
Yeah, we were, Joanne and I were talking about that. We think that theoretically, at least, our outreach on the video channel may be larger than our outreach in person. So at the very least, we want to keep this video chat going, and we can talk about, as those of us in the Chicago area can talk about whether or not we want to take some of this back onto the physical sidewalk, Sidewalk Science. We had a lot of fun with that about a year ago before the pandemic.
But again, if we talked with half a dozen people at length, we thought that was a good day.
Mm-hmm.
Whereas we can talk with any number of people, at least hypothetically, right here. I believe we've
already got half a dozen watching.
So. A dozen watching. It's supposed to be 12 today, and maybe 15. So this appears to be a better medium for.
I like the side. I like the interaction with people too. So, but the problem is limited time. But you know what? One of the other things is Ivan and I have kindled our friendship I think, in the past year during the pandemic, and we're both in the Chicago area, so maybe we can meet up somewhere physically and do some sidewalk science or street epistemology or something. So who knows what the opened up world has for our future as science advocates.
I'll drop in a completely non-scientific.
Yeah, what's going on?
now. Today, I launched book 6 of Sexuality Chronicles. That the title is Gilles Rain and the Two Cities. It's up on Amazon. Anyone who'd like to buy it, please, Joanne Reed. You'll find me.
R-E-I-D.
R-E-I-D.
Congratulations. Congratulations.
I have read the first 5 books, and I'm a fantasy fan from a long time ago, you know, Tolkien and whatnot. I got to say, I'm not just saying this as your friend. I've genuinely enjoyed the books. I think they're excellent. They've got great military strategy. They're fantasy. You know, you don't have to worry about getting the science right in a fantasy book.
That's right.
And so they're really fun.
Because there's magic, and therefore it is not science.
Right.
Not even close.
Is there going to be a volume 7 and 8 and 9 and 10, or are you doing something else?
The most recent will go through volume 7, and then I have to start a whole new series. I've begun it, and I'm not sure how many it will be, but I will take up the time between the book 7 and the first book of the next series by putting out paperbacks. So I got 4 paperbacks I have to put out.
Right, and then Ivan recently has a book published as well on essentially how to do reasoning, sort of a formal guide to how to do reasoning, textbook rationality, I believe.
There it is.
Wow.
There it is.
And Ivan, you're going to be joining us next month for one of our Science Sunday programs, which is a program on the days following Sidewalk Science. We have Science Sundays, and Ivan's going to talk to us about his book for a whole hour next month. So
Looking forward to it.
Congratulations to Ivan as well.
Thank you.
Yep. All right. Well, without further ado, let's talk about today's topic. Typically on Sidewalk Science, we choose a focus topic, and there has been some science that's been all over the news in the past couple of weeks, and I thought maybe we'd focus on that today. And that is the science of the marvelous muon, a magnetic muon, nonetheless. And so we're going to talk about the muon.
Which has nothing to do with cows, by the way. No.
Oh, man. Yeah. Okay.
Mike, you want to rev us up and talk to us? What the heck is a muon, and why do we care about it?
All right. So let me kick off. It was a lot of hype. My sister in London called me up. I mean, she said, it was on the BBC. What's this about Fermilab on the BBC? And then it was all over the New York Times and everything like that. It got a huge amount of publicity. And it is important, but it's good to see. I mean, so what is a muon? I mean, the muon was first seen in cosmic rays in the 1930s, but it was very confusing about what it actually was until the 1940s, when it was realized that there are actually 2 particles like the muon in the cosmic rays. One is the muon itself, which is a heavy partner of the electron. It's about 207 times heavier than the electron. Otherwise, it seems to be very much the same in the sense it's got exactly the same electric charge as the electron. It comes in positive and negative varieties like the electron does. It has the same spin, which is angular momentum. Actually, don't think of it as a spinning ball, because it's not really a ball, it's more point-like. In fact, it's at most 1,000th size of the proton, and maybe 1,000,000th, or maybe much even smaller still. So it's not really a ball, but it has angular momentum or intrinsic angular momentum. And because it's got charge and angular momentum, that makes it a little magnet. The electron's a little magnet as well. And the magnetic field is particularly interesting because, as you probably know, the magnetic field is like photons, virtual photons in a cloud around the electron or around the muon. Now, a friend of mine, actually, I couldn't call him a friend of mine, Jerry Gabrielson in Harvard. He's a very clever physicist. And some years ago, he measured the magnetic moment of the electron very precisely. And he did this by making an atom with Z number 0, in fact. So, you know, the simplest atom we think of is a proton with an electron going around it. he got an electron to go around in an orbit around magnetic lines of force in a bottle. So he trapped a single electron in a bottle, and it was orbiting around the lines of force like it would orbit around a proton if it was in hydrogen.
That's purely due to magnetism, though, right?
Purely, I mean, it's the electron in an orbit around the lines of force of the magnetic field, and it could actually jump up to higher excited states and fall down again, emitting photons and absorbing photons, like a normal atom does. And he could repeatedly observe these transitions of this electron in orbiting thing, and measured the magnetic moment of the electron extremely precisely. I mean, I think to 1 part in 10 billion or something like that. Very clever stuff on a benchtop. And it agreed with theory very well. Now the muon, who ordered that rubbish? We don't, why is there a heavy version of the electron? And actually there's an even heavier one called the tau, which makes a triplet. There are 3 of them: electron, muon, tau. There are also 3 types of neutrinos that go with these. Why 3? Well, theoretically, it seems that in order to have a matter-antimatter asymmetry in the universe, which we call CP violation, charge parity violation, you have to have 3 families of these particles. If you just had the one family with just the up and down quarks, the electron and its neutrino, nothing else, then theoretically, they don't see how you could have a violation of matter-antimatter asymmetry, which we don't really understand. But anyway, so maybe the existence of the muon is something to do with matter-antimatter asymmetry, namely matter dominance in the universe, namely we can be here. But anyway, so now the muon magnetic field, you can't do the same thing as you did with the electron, because the muon decays and you can't keep it long in a little tiny bottle, but you can keep it in a ring, like think of a vacuum pipe bent in a ring that's actually got a radius of 14 meters at Fermilab, and the muons can go round and round, and because they're going fast, their internal clock is slowed down, which means they live longer than they would if they were sitting at rest, and you can actually get them going around hundreds of times, decaying on their way as they go around. That was first done at CERN, actually, in the 1960s, while I was doing my PhD, actually, and by a small team, and they managed, and they could see, as the muon goes around this orbit and it's decaying, what it does is decays by spitting out an electron and a neutrino. So the muon decays to an electron and actually 2 neutrinos. But anyway, the electron that comes out, and they could measure the electron coming out, and they could see that as the muon goes around this ring, the signal of these electrons coming around up and down in a wave, because the muon is actually, as it goes around, its magnetic field is precessing. That is like a gyroscope. If you spin up a gyroscope and put it at an angle on a table, it won't stay at that angle. It will go round, precessing around. Now, a muon will do the same thing, but in a magnetic field because of its magnetic moment. And so that was a pioneering experiment. And then it was redone at Brookhaven with a new ring, and they got a result which disagreed with the calculations, the theorist calculations. Now, what are the theorist calculations? So Dirac first, who had the Dirac not only invented the idea of the positron, but he also developed what we now call quantum electrodynamics, the quantum field of electromagnetism. And he said he could calculate the magnetic strength of a muon in terms of 3 things, basically. Its mass, its electric charge, and Planck's constant, h, which is the relationship between energy and frequency and so on. And there was a factor of 2 in his equation. And it was 2 because the spin of the electron, of the muon is, or electron in that case, is half. So that so-called G factor is the number that goes into the equation calculating the magnetic strength of the muon. And it's 2, according to Dirac, it's 2. Now, along comes people like Feynman, who could calculate this much more precisely using fluctuations in the vacuum. So when you think of a muon, it's got this cloud of photons around it, the electromagnetic field, the magnetic field of the muon.
Does an electron have the same kind of cloud?
The electron has a cloud too.
Okay.
But they're not identical clouds because the mass of the muon is much heavier than 200 times more than the electron, which makes it easier for the muon to have heavier particles in its cloud. Like the muon can even have like a W boson in its cloud. Now, a W boson is very, very heavy, but it can exist for a tiny fraction of a second by the uncertainty principle. So actually, in among all the diagrams, they're called them Feynman diagrams. Feynman drew these nice diagrams of particles shown as lines and photons as wiggles and stuff. And you add up lots and lots of diagrams, all the possible ways that you could have these virtual fluctuations of electron-positron pairs, or pion pairs, kaon pairs, and so on in the cloud. Now, because the muon is heavier than the electron, it does have actually a much bigger content in its cloud of heavy particles like W and Z bosons. It goes like the square of the mass.
Oh, wow.
And because the mass is 200 times heavier, it goes like 40,000 times more. So the W contribution is very, very small, but it's still 40,000 times more in the muon than in the electron. So you would expect the muon to have a different composition of these virtual particles in its cloud. And that means that the magnetic moment of the muon is going to be a bit different from the electrons. In both cases, the difference is a small compared with 2. So what one usually does is subtract 2, and the difference from 2, which we call G minus 2, that's the anomalous magnetic moment, it's so-called. So theorists then are able to calculate using big computers and a lot of computing time and lots of these diagrams, these so-called Feynman diagrams, putting into the cloud not only electron pairs, muon pairs, W. Now, the muon and the electron, in principle, can fluctuate to a W and a neutrino and then reabsorb them and go back to muon. It's a very unlikely thing, but it comes in at some deep level there. So,
so Mike, can I interrupt you with a question?
Yeah, sure.
So it sounds like, as you zoom in closer and closer and to ever smaller time scales, looking at an elementary particle like an electron or a muon, as you zoom in time and space, instead of looking like a particle, it looks more like a chaotic cloud of reactions happening with all of these possible ways that the physics allows particles to transition into another particle or into more than one particle and then back again. And all of this chaotic stuff is happening in kind of a fuzzy cloud, near a zero point, the zero radius of electrons and muons. And that cloud looks different for a muon than it looks for an electron because they have slightly different properties, especially their mass. Is that a good way to summarize it?
Yeah, I think that's a very good way of thinking about it. I think it's a right way of thinking about it. So, you may say, if I look at an electron with a microscope, what do I see? Well, of course, with a visual optical light, you can't see it much too small, but you can make the light wavelength much shorter, making gamma rays and shorten higher and higher energy gamma rays, make shorter and shorter wavelengths, and you can start to see if you can see any structure for the electron or the muon. Now, when you do that in your head, or sort of experimentally, you can do it, as you zoom in, by increasing your magnification, which you do by increasing the energy of a gamma ray, you start to see the electron or the muon not as an extended object, but being surrounded by a cloud of these virtual fluctuations, an electron-positron pair, or a muon pair, or eventually a W. Eventually a Higgs can be seen popping out but disappearing again quickly. And it's sort of all due to Heisenberg uncertainty principle. But the muon, being heavier than the electron, you can zoom in farther, if you like. You can go down to smaller distances.
Oh, okay.
And see things more massive by going to smaller distances, which means smaller times as well, in a sense, space and time together. So that's how it goes. So actually, there's a big consortium of theorists who, since the Brookhaven result, so the Brookhaven result said, okay, we see a difference from the theory by what it's level called three standard deviations or something. I mean, the theory has been evolving a little bit, but a consortium of theorists, I don't know, 100 of them, tried to put together everything they knew about the standard model of particles into these calculations. And so they've refined their calculation. And meanwhile, this ring, this big magnet ring, was brought over from Brookhaven by sea down the coast and then up the Mississippi and through roads to Fermilab, where it arrived. I've got some pictures I can show if I share my screen, but it's quite a feat of engineering as well as physics to do it again, and to do it better by measuring the magnet, by making the magnet more uniform, by measuring it more precisely, by using more muons, because Fermilab could produce more muons. Oh, we produce the muons. How do we do that? We take a beam of protons and we send a beam of protons into a metal target, and the protons hit the nuclei and produce pi mesons. Okay, they're the quanta of the nuclear force, if you like. And the pi mesons then decay to a muon and a neutrino. Okay, and the neutrino, you don't see it, goes off, but the muon can be captured by magnets and injected into this ring, and they go round and round and round the ring, wobbling in the magnetic field as they do so.
Is this the same ring that the Tevatron, the famous ring at Fermilab, or is it a different ring?
No, yeah, it's a completely different ring. I mean, the Fermilab ring, that's a kilometer in radius, 4 miles around. This one is 14 meters in radius. And it had to be brought as a whole thing from, because it's a superconducting magnet, had to be brought as a whole on flatbed trucks and stuff like that. When it arrived at Fermilab, about 1,000 people came to see it, welcome it arriving there. And if I share my screen, can people outside see it if I do that?
Yeah, we have to wait just a second for Dave to hop over to the other computer. Dave's our technical facilitator and sometimes panelist. So he's got to go to a different computer and make the sharing.
We call him the man upstairs.
Yeah, he's
upstairs.
Well, I can talk a bit. I'll talk a bit more until he's ready to let me share the screen.
He'll message me when he's ready.
Okay, fine. So what happened then? So this new team with better particle detectors. So they've got the muons are injected and they go round and round many orbits around this ring. The muon lives its average lifetime. Let's say I had to write this down. So the lifetime of the muon is 64 microseconds if it's sitting at rest. 64 microseconds. So it'll go around the ring a lot of times. But actually, because they've got an energy, they're going faster and faster. Time dilation makes them live for 700 microseconds. So,
oh, nice.
So they go around many times, decaying as they do so, and wobbling as they do so.
Dave says he's ready for you to share, by the way.
Okay, so let me now share screen, and you should be able to see this picture.
Yep.
Okay. So this is now the ring Fermilab. There was a special building for it. So that whole ring had to be lowered in, take the roof off the building or put it down there, reset it up. And around the inside are particle detectors to detect the electron that is spat out from the muon when it decays. Now, the muon, when it decays to an electron and a neutrino, it doesn't do that in all directions equally. It does it mainly along the spin axis and in one particular direction. That is actually a parity violation thing. So they pick up electrons with a certain energy as they go around the ring.
Electrons or muons?
They pick up the electrons from the decay of the muon. If you
okay,
like.
got it.
Actually, they're positive muons, so they decay to positrons, but they detect the positrons coming out of the muons. Those the muons that don't decay keep going round and round, but they decay on their way. And they then measure the signal that they see. And of course, one bunch of muons then decays away, and with an average time of 700 microseconds, which is less than a millisecond. But what they do is they put another bunch in, and then another bunch in, another bunch in several times a second, and build up statistics on that. And then they can end up with, oh, here's a picture, here's a diagram of this ring. You've got, it's not so simple. You've got quadrupole magnets, which are magnets that have 2 north poles and 2 south poles, making a 4-fold symmetry field. They're used for focusing, to keep the muons focused. And it's a clever thing that because the muons are not absolutely parallel to their path of direction, they have like a spread. That would complicate the thing, except there's a magic momentum or speed where they go, where it's sort of minimizing that effect. Anyway, so here's now from their paper that came out just a couple of weeks ago, measurement of the anomalous precession frequency of muon in the Fermilab muon G-2 experiment. And this is the key magic plot. You see here, this is the number of counts of electrons that they saw as a function of time after injection. And it's going down because it's decaying. And then they flip back over here like a TV, like an old TV raster thing. You know, it's coming down here and down here and down here. And as it goes, and this is because muons are decaying, the intensity is going down and down. And because they have so many muons in, they can measure this wobble over a very large number of cycles, if you like. And the more cycles you measure over, the more precisely you can measure the frequency. Over here you see I've shown a couple of Feynman so-called diagrams, and you see here's a diagram showing the muon traveling along, and it's hitting a photon in the magnetic field of the magnet, actually. But it's done before it hits that, it's emitted a photon, which has turned into a quark-anti-quark pair in this case, and then been reabsorbed. And there's another way of this diagram can happen. This blob here is supposed to represent the sum of things like a pi plus pi minus pair or a k plus k minus pair. And these
Mike,
are things that are hard to calculate. Yeah.
I have a request. Can you make that whole PowerPoint window a little smaller, maybe? On our YouTube channel, it's only showing up as the text part. So make it a little smaller, and then I'll see if it shows up on YouTube correctly. Yeah, right about there. Yeah, that works fine. Thank you.
Okay. So yeah, so what I was saying, on the right hand, you see a couple of these 2 out of 100 or more Feynman diagrams that have calculated that this represents the magnetic field. This line represents a muon going through space, and this little wiggle represents a photon being emitted from the muon, turning into mesons or hadrons, pions, and then being reabsorbed. And these are the things that change the muon magnetic field. And over here on the left, you see the wiggles as each up and down represents one precession of the muon in the magnetic field. And the important thing to measure is the frequency of those wiggles. And of course, the more wiggles you can measure, more precisely you measure, the better you can measure the G-2. Now, is G-2 because if it was exactly 2, if the difference from 2 was nothing, then it wouldn't precess in that same way. It would actually, anyway. So there you go.
So if this quantum fuzz, due to the Heisenberg uncertainty principle, if this quantum fuzz did not exist around either electrons or muons, it would be exactly 2. Correct. But the quantum fuzziness, which is very slight in our universe, in some sense, fortunately, that quantum fuzziness sort of adds a correction into that 2 and displaces it either to the right or left of 2. I think it makes it a little smaller than 2, if I remember correctly.
It makes it a little bigger, actually.
Bigger? Okay, sorry.
Yeah, but and the measurement is well, the difference from 2 is measured to 11 decimal places. It's 0.00116592. It's very precisely measured and calculated. But now comes the key point. The fact that this difference is now been confirmed from the Brookhaven experiment. And so far, Fermilab's only released about 5% of the data they have actually in the bank. They've got more in the computer. So they've got a lot more to come. But their result agreed with the Brookhaven result, a little bit more precise than the Brookhaven result, but not much. But when you combine them, you now get an effect that they say is a bit above 4 standard deviations. And we have a sort of benchmark that 5 standard deviations in particle physics is a real discovery. You can't doubt it really, but 4 could be. Now, actually, I think it's part of our law, but it's very important when you're looking for a bump in a mass distribution or something like that, when you've got hundreds of bins you look at, because some bins can easily fluctuate. But when you're looking for a single number, one number, this is G minus 1 number, I think it's a stretch to require 5 standard deviations. 4 is perfectly fine in my view. So I think it's absolutely real effect, and it shows that the Brookhaven group didn't screw up or drop, miss something out. Now, what does that mean? It means that in all these calculations a theorist done, where they put in all the particles that we know about in the Standard Model, the electron, the muon, this tau, the quarks, the W and Z bosons, and so on, they don't, unless they've missed something. There's something else there. And now, I think it's not new that there's something else, because we have the mysteries of dark matter, for example, which we think is, we're pretty sure dark matter is there because it's got gravity. And it holds galaxies together. But it's conceivable that dark matter doesn't have any interaction with the particles that we know and love, like electrons and muons and so on.
Through the forces that we also know and love.
And the forces that we know and love, that's right. So, I mean, dark matter could conceivably be particles like mirror particles or supersymmetric particles that interact among themselves, but not with our particles. Now, this shows that at least something is missing that does interact with our particles at some level through interacting with a photon, that's electromagnetic coupling, or with a Z or W bosons, that's the weak coupling. But it does mean that we are missing something, almost certainly a particle or particles that do interact with the particles we know and love in the Standard Model. And we have to find them. Okay.
So now, can I paraphrase a little bit again?
Sure.
So it sounds to me like the implication is that this fuzzy cloud of particles that pop in and out of existence, according to the laws of physics and the laws of the universe, this cloud, we thought we knew what was in that cloud. We thought we knew about the W and Z. We thought we knew about the electrons and the quarks and the Higgs and so on and so forth. But this may be evidence that there's something else going on in this cloud in terms of a particle interaction and a particle species that no other experiment has ever found evidence of. Is that correct?
That's correct. Now, some people could have said maybe the dark matter is not real particles at all, but little black holes or little grains of dust or pebbles or whatever out there in space.
Or lots of Jupiters. I've heard that too, trillions of Jupiters.
Astronomical. Now, I'm not saying that this proves that it isn't that, but it does mean that there's something that is particle nature that is missing in the Standard Model, and that we're looking for, at the Large Hadron Collider. And I'm happy to say I had a meeting with my colleagues yesterday with the top brass of the CMS detector, and I've been proposing a new search for new particles that could be something to do with this, and they didn't pour cold water on it. They said, well, we should talk to the Large Hadron Collider people about it. So I'm encouraged by that. I mean, don't hold your breath, because if this happens, it won't happen. We won't get data for another 6 or 7 years, but we could in principle look for things like so-called dark photons that could be part of this business. A dark photon is theoretically a particle that's like a photon. It does couple to electric charge, but much more weakly than electrons and muons do. Okay, so it's, and it's not zero mass, it has some mass, small mass. Or there's thing called a heavy neutral lepton. What's that? It's like a neutrino, but neutrinos are extremely light. But theoretically, they could be neutrino-like particle that is actually got mass. It could have 2 GeV, 3 GeV. It could travel through blocks of steel, and then it could decay to an electron and its own type of neutrino, things like that. So my proposal is to look for particles created in the LHC collisions that can, in the forward direction, that can go through 50 meters of steel into a big vacuum tank and decay in this vacuum tank to particles that we know and love, like electrons and muons and taus and so on. Anyway, that's by the way, but this is exciting for me because it does mean that there's some new particles there to be found. And there's lots of other experiments looking for them, but the one I'm proposing with colleagues it's got a unique window in terms of its mass and its coupling strength and lifetime, if you like. I mean,
well, I'm rooting for you.
Meters, but and go through steel. But anyway,
this could be huge. Yeah, fantastic. Thanks, Mike. Well, I gotta comment though. As I've read up on this the past couple of weeks, I have
following up on this as much as we could.
Yeah, I did see an article by some theoretical physicists who have thrown a little bit of maybe not cold, but chilled water on the enthusiasm. They've said that it's actually the calculation that's off to begin with, that they tried a new method for calculating using, splitting space and time up into really tiny cubes, as it were.
Yeah, running the computer stuff crazy.
Yeah, and then simulating the status of space-time, the energy and momentum and particles in each of those little cubes. They've sort of really magnified from a theoretical computational perspective. They've really tried to zoom in on what's going on in that cloud, as it were, and they've come up with a different result than is being treated as the conventional result. And again, this is just a group of a few physicists, a few theoretical physicists who used a computer to simulate and do this calculation. So it's not definitive, but it's at least a little chilled water on the enthusiasm that says, well, maybe it's not the physics that's different. Maybe it's our calculation that was off to begin with.
Right. No, this is exactly true. And the biggest within the standard model, if you have no new particles, the biggest uncertainty in these calculations is exactly the coupling of the pion to the photon, if you like. I mean, from a long distance, the pion has got an electric charge and so on. But how does calculating the masses, we can calculate somehow the masses of these particles, but it's very hard, and it's not been able to do that except in what's called lattice gauge theory. Now, what does that mean? It means let's forget about trying to calculate the masses of these particles from the masses of the quarks, if you like, in continuous space and time. But let's see if we can do it by assuming that space is actually, that we can calculate on a grid in space, right, and a grid in time as well. So let's divide space up into a grid, like a fence, a wire fence, if you like, and we can calculate the strength of coupling between points in space, and we can make the points in space, 10 to the minus 13 centimeters apart, or 10 to the minus so. And then in time as well. So you have a space-time lattice. It's called lattice gauge theory. You approximate space and time, which we know are continuous, at least at this scale, they're continuous things, but approximate it by a lattice. And then they can do the calculations. And then, of course, space is not like that. But they can say, let's redo the calculation with a lattice spacing that's half as big, and then a quarter as big, and then an eighth as big, and see if we get the same sort of results, if it's stable, and then pretend to extrapolate to zero spacing. Now, this way they do calculate what they think is what's called the hadronic contribution to this muon cloud, the cloud around the muon, because but it's the most uncertain thing in the thing, because these pions are extended objects, and of course you're not talking about real pions but you're talking, it's complicated. Okay. But, yeah, I did see that. I mean, there've been many papers coming out about this. Obviously, people have been preparing their papers ahead of time, waiting to plug in the number at the end, But one of them was saying that perhaps that lattice calculation of the pion form factor, it's like the shape of the pion as seen by photons, that could be wrong enough that this result could actually be not requiring any new particles. But okay, so that is a caveat. Yes, it's a caveat. So it's still saying that the calculation wasn't done correctly, but not with new particles, but with a new calculation of the old particles, mainly the pion.
Okay.
Comes in. Yeah.
Will this be resolved by continuing experiments on Fermi, for instance, additional data?
Well, Fermi there's got more data. They've got more data in the bank, and they'll come out with that. And I'm pretty sure what will happen is it will reduce the uncertainty on the experimental value, but it won't get it near the theoretical value, you see. So the discrepancy will stay there. But one thing you can say positive about this, apart from just saying, well, there's something new, is that assuming that it's not this hadronic calculation of lattice gauge theory, it limits the possibility about new particles, because theorists have been going crazy thinking of all sorts of new particles, dark this, dark that, and so on and so forth.
Axions and supersymmetric particles.
Exactly. And this is limiting them because some of their ideas aren't compatible with this muon G-2 result.
Okay.
There's one thing I've been thinking about a little bit is if you could possibly measure the G-2 of the tau. I mean, the tau's like a muon, but heavier, okay, more massive. And of course, they don't live long enough. They only live they can live for a few millimeters when you make them in a collision. You can't get them in a storage ring. But this is just a thought, and it's half baked. But you can produce a tau plus and tau minus pair by putting a high energy gamma ray into a sheet of gold or lead or iron or something like that, and you can make tau pairs. Now, those taus, on their way out, they pass by a nucleus of gold or lead or whatever, and that nucleus got a strong magnetic field on it. So it's conceivable, it's just a thought, that you could get a measurement of the tau magnetic moment by studying tau pair production in a gold foil or something like that. Now, you won't get anything like the precision of this, but the tau magnetic moment could have an anomalous magnetic moment that's thousands of times more than the muon one. So,
okay.
Anyway, I'm going to talk to some theorists about it, and they'll probably say, "Mike, you're full of rubbish," So, but it's a thought. It would be, how could we measure the tau magnetic moment?
So there's another experiment that hasn't gotten quite as much press, but I've read that CERN did an experiment where they were trying to generate muons and electrons from a single sort of decay process. And their theory predicted the ratio between electrons and muons that they should see as a result of these collisions. But when they went to measure it, they found that there was an anomalous number of muons produced. So this is a completely different experiment.
Like 3/4 of what they were supposed to be?
Yeah, having nothing at all to do with the magnetic moment of the muon, but further evidence that something strange is happening in muon world. So do you know anything about that?
Right. Yes. So, and the result, they came out with a result. I mean, it's been out a bit earlier, but a new measurement that about the same time. So it's a great experiment. It's called LHC-B. The B standing for the B quark, which is a heavy quark. It weighs about 4 GeV. Discovered by Leon Lederman actually at Fermilab actually. So the B quark then is very unstable and decays. And one of the decays is to a strange quark, which turns into a K meson, and then a pair of electrons or a pair of muons. Now, they're rare decays. They happen, I don't know, 1 in a billion or something like that, but they have got a lot of them. So they say that they expect a certain ratio between this B meson. So it's a meson. The B quark actually joins hands with an up or down or strange quark to produce a meson, but it's the B quark that decays. And it can decay to E pairs or a kaon and E pairs or mu pairs. Now, so this is the B quark. So now, what I've heard, I mean, so on the news, oh, we expect exactly the same number of E pairs and mu pairs coming out of these decays.
Right.
And I don't think that's correct because there's a thing called phase space. The muons have got more mass than the electrons. And so there's less momentum space available to the mu pair than to the E pair. But I'm sure they've taken that into account, you know. But that does mean that the ratio should not be exactly 1, but it should be fewer mu pairs than E pairs. And I'm not sure what the ratio should be now, and they are finding a discrepancy, and I think they're finding more mu pairs than they expect. Or do you know, is it the other way around? I'm not sure which way around it is.
I think it was 75% of what they were expecting.
I've got a computer in front of me. I can look up to see what
We can
the
look it up.
Yeah, so that's another anomaly, and there are other anomalies out there, but that is not the 4 standard deviation level. I think it may be 2 or something, but it's worth following up on. And in turn, that also got on the news, and they're talking about a possible thing called a Lepto Quark as being responsible for that. Now, I think that is 1 out of a dozen possibilities if it's true, you know, if it's right. But a Lepto Quark, what that is, it's a particle that's got the quantum numbers of an electron or a muon or tau together with the quantum numbers of a quark. So it's got a fractional electric charge, but it's got no spin because the spins of the lepton and the quark cancel each other. Because it has no spin, that means it's a boson, like the Higgs. I mean, it could have spin 1 if they're parallel to each other. It could, in any case, it's a spin 0 or spin 1 object if it exists. And that makes it look like a force carrier, if you like, because force carriers like the W and Z, the photon, the gluon, they've all got spin 1, and then the Higgs is spin 0, and the graviton, if it exists, is spin 2. But integer spins is force carriers. So a lepto quark can be considered force. Well, actually, a pion, if you like, is 0 spin. It's got 2 quarks in it, a quark and anti-quark, with opposite spins making 0 spin. The pion, it's a force carrier. It carries the force between protons and neutrons in a nucleus, you know? So even spin things are force carriers. So that's how this word fifth force came about. That sounds, you know, pretty sexy, a fifth force, you know, but actually I think that's a bit of hype because we do know particles with spin 0 and they are force carriers, but they're not, I wouldn't call them a new force beyond the standard model, you know? See what I mean?
So, you know, I want to highlight a couple of things for our general audience about forces of nature and the fifth force and whatnot. There's an excellent book that I've read by Sean Carroll. And in that book, he talks about, he makes a point. He says, every force of nature that is relevant to our everyday world, whether it's picking up an object or launching a spaceship or understanding how sunlight is generated, every force of nature relevant to some macroscopic effect that we recognize in the natural world, all of those forces have been discovered, right? So when people talk about things, he especially references this in regard to things like ghosts or you know, mental telepathy or other things where people without a science background speculate that maybe there's some new force of nature that is new energy, new way of transmitting energy and whatnot. And Sean Carroll makes the point that if there were a force of nature, and physicists generally like to couch that in terms of interactions rather than forces, for technical reasons I can explain if there's a question about it, but if there were a new fundamental interaction in nature that affected atoms or even electrons that we use for things like electric current and whatnot, if there were a force of nature that affected large bodies and we could use for communication over distance and whatnot, we would have found it with all of the particle experiments and everything else we've done. So when, right, yeah, exactly. So when people nowadays are talking about a new force of nature potentially associated with this muon anomaly, perhaps a better way to state that in terms of vocabulary and conception is to say there's a new interaction, and that interaction would necessarily be mediated by a kind of particle that has never been seen before. Probably a very short-lived particle, probably a massive particle, and that new interaction might have some implications for super microscopic physics, like happens at the beginning of the universe, when the universe was compact and hot and dense, and there was enough energy around to make these kinds of interactions far more common. Maybe there's a link there between the initial cosmogenesis, the creation of dark matter, from the initial energy fields and potential fields permeating the universe. So there could be a little wedge that we could stick in with this new discovery that helps us find a relationship to how dark matter relates to other manifestations of matter and force in the universe. But it's not a new force that you could use to, to communicate necessarily, or to move objects with your mind or with anything else. It's not that kind of force. It's a new interaction that only rears its head in very specific circumstances.
My mind has a difficulty of waking up in the morning. So,
well, I mean, I go along with that a long way, Scott. Not all the way, because I remind you that we only know about 5% of what there is in the universe. We know there's dark matter, which we don't know what it is. Okay.
and dark energy.
And then there's dark energy as well. Now, dark energy, it could just be, a number in Einstein's equations, a cosmological constant or something like that. It could also be something with particles associated with it. It could have more than one particle associated with it. Now, so we just don't know about that. Now, I'm not saying that dark energy, it's so low density, and we can calculate the density of dark energy per cubic meter and so on, but it's not going to affect everyday life like moving atoms around or electrons around. But it could have effects that one effect is that it seems to be blowing the universe apart, getting, accelerating faster and faster. So that is, it could just be, space expanding somehow, but it's mysterious. Now, I have a private theory about dark energy that is actually made of particles, and they're actually tachyons, and which are particles that always travel faster than the speed of light. But they're so low in my ideas, they've got such a tiny mass, which is imaginary in the sense that two tachyon masses squared is negative, so they repel each other, but extremely tiny. But who knows? That's I'm not saying we know all the forces. I think we know pretty well. We're pretty sure there are forces that affect everyday matter. But yeah, and
I'm just saying that this is not a gateway to things like ghosts and ESP and other things that sometimes people who aren't very well versed in science, they use the word force or energy in the context of, well, there are forces that we don't understand. Well, there very well could be an additional force of nature that we don't understand. But the likelihood that that has anything to do with what you want it to be about, which is ghosts and ESP, and right,
small,
right. So it may be relevant at cosmological scales or subatomic scales, but it's not,
or early universe scale.
right. But it's not relevant to your kitchen. Yeah.
Well, I don't know. I mean, yeah, I'm a bit humble about that in a way. I'm thinking of applying for the James Randi Prize for telepathy, which is now over $1 million or something like that, if you can prove it. So here I have this experiment where it makes it physically impossible by any of the known forces for people to interact with each other, or send information faster than the speed of light. But what about feelings? I mean, actually, spoiler alert, this is my science fiction story coming along, Joanne.
Oh, nice. Good. All right. I did find in the news article here that the experiment at CERN where they expected to see the same number of electrons and muons produced, they found a 15% discrepancy with more electrons being produced than muons.
Okay, well, more electrons and muons is what you expect just on the grounds of there's more momentum space available because the electrons are lighter. So it's that way round, but I'm sure they have used that. It's called the phase space factor.
Yeah,
They've used that. So, but that would give you more electrons and muons, I think, naively. Now, there's another thing about that's different with electrons and muons to bear in mind, and I don't know if it's relevant, but there's the Higgs coupling. The particles coupled to the Higgs boson. The Higgs couples to particles according to how heavy they are. The mass couples to Z bosons, top quarks better. We have seen evidence for it coupling to mu pairs in CMS, that is Higgs decays to mu pairs. Not 5 sigma yet, but there's evidence that it does. But it couples to electron pairs much less because the electron's so weaker. The decay of a Higgs to mu pairs is very hard to see and much more likely to go to charm quark pairs or bottom quark pairs. An electron is 200 times less likely than a muon pair. So we're not sure we'll ever see the Higgs. But this means that the Higgs muon couples to Higgs more than the electron does by 200 times. So, you know, and some people think there may be another Higgs, a sort of hidden Higgs. A Higgs that is, you know, maybe its mass is 10 GeV or something like that. And it couples not much to our particles we know and love, but to other hidden particles. So, you know, this is one of the many possible ideas.
Yeah, John made this point when we were preparing for this topic today. John made the same point that you did, Mike, that, you know, for all we know, considering everything we know about the way the universe works, the stuff we know predominantly is about 5%. It's regarding 5% of all the stuff that exists, we think. You know, when you take into account dark energy and dark matter. So there's this whole, physicists have this term they use, they call it the dark realm. And the dark realm is the realm of dark energy and dark matter. And then
the other 95% of the universe.
Right. The bulk, as it were, of everything that exists. And physicists have had a lot of fun speculating about possible dark forces. And, you know, I always pictured Luke, I am not your father, you know, that sort of dark forces. But, you know, it's at least within the realm of speculation. There's a certain plausible argument that can be constructed that dark matter may have an interaction, a set of interactions that are unique to dark matter, besides gravity, which is the way it interacts with regular matter.
Well, you know the story of the drunks under the lamppost, right? We in physics we have this tremendously bright light on particles and their interactions, which is called the synchrotron. And this muon result is a synchrotron result, and most of the results we've been talking about have been synchrotron results. The trouble is that once we get away from the synchrotron, we don't have street lights that are nearly as bright, and there may be a lot of stuff out there in the darkness.
Yeah, let me remind you, John, that the electron magnet moment was measured with a cyclotron, not a synchrotron, in a in a vacuum tank. You know. Anyway, you're right. But so, I mean, yeah, it's certainly conceivable that dark matter is something that may interact among itself and make even atoms and molecules among itself, but they don't interact with normal matter except gravitationally. You know. So
one of the things that cosmologists, I think, have I want to shy away from the word concluded, but one of the arguments that cosmologists have presented is that dark matter, if it does interact with itself, it interacts with itself much more feebly than normal matter interacts with itself. So that we call normal matter baryonic matter, right? It's just a special term in physics. So normal matter interacts with itself readily.
Normal matter.
Right. And glasses of water and human beings and biology and all of the complex molecular interactions that normal matter can exhibit, that entails a kind of clumpiness that some cosmologists have said there's not much evidence that dark matter exhibits any tendency towards clumpiness, except with the possible exception of primordial black holes. So it may be that some of the black holes formed early on in the universe, consisted of dark matter. We don't know, right? Gravity is gravity. You can't tell an elephant from a star once it's swallowed by a black hole. Matter and energy is matter and energy. So in any case, there's at least some cosmological arguments that say that dark matter probably doesn't exhibit a lot of tendency for structure and interaction, but I don't think that means it's zero either.
Yeah, the most baryonic matter in the universe is in the form of gas and plasma, and that undergoes long-range interactions through magnetic fields, through shock waves, through a bunch of different phenomena that allow it to get rid of its kinetic energy and condense into disks and stars and planets. And it doesn't seem like that sort of condensation is happening with dark matter right now in the universe at present.
But we know that dark matter is not completely uniform through. It can cluster in galaxies. Otherwise, it wouldn't affect the galaxy rotation.
Right.
So
that's correct. It seems to it seems to be like the stars in a globular cluster. It seems to form diffuse, nearly spherical conglomerations of matter due to gravitational interaction. But the reason that you get disks and stars and planets and all that is that normal matter has these interactions that allow the matter to get rid of its energy while keeping it does keep its momentum. And so it collapses into these rotating disks, and then the disks collapse into smaller disks and clouds, and you get, the whole thing that all the universe we see with telescopes basically comes out of that. But the dark matter doesn't seem to go through this next stage. It clusters as if it was just non-interacting particles.
Yeah, and if there were a lot of dark planets around flying through the solar system, they would perturb the orbits of the planets we know and love, and we don't see such things, which doesn't mean they don't exist, but it means they're not very common, right?
Right. So the dark realm, as it were, may have some sort of complicated physics, but it's probably not complicated enough to allow for biology or complex chemistry. But I don't know. I could be completely wrong too, because we just don't know a lot about it. We have a question from a viewer. I want to ask Ivan this question. Make sure, Ivan, you get to talk about some of these topics as well. I know that you have a background in theoretical physics. We have a viewer who said, can we make sort of, instead of electricity, can we make muontricity? Can we do something with muons? Can we make electricity out of it? Can we do something practical with muons? Is there some goal of studying muons? Why are we looking at it? Is it something that we can build some technology with? So Ivan, what do you think about that?
So the reason that we can't.
I can tell you how.
Oops.
Oh, sorry, I was getting some feedback there. The problem with muotricity is that muons are unstable. My memory is failing me. I thought the lifetime was something like 2.2 microseconds, but you said, Mike, that it's about 64 microseconds, right? So that's very different from when you have a metal. The metal has electrons that can move around, and that's why you have a current. You can create a current in metal, but the electrons are stable. They won't decay. Muons are unstable. So after a few 64 microseconds, most of the muons are going to be gone from the metal, and you'll have a ton of radiation pouring out.
Oh, that's bad, right?
That's generally bad, considered bad, yes. They are important, an important factor in cosmic rays. So we have muons showering down on top of us from radiation from space all the time. So it is an important factor when you're building equipment and you need to care about noise from radiation. But mostly in this context, we're using it a little bit like a microscope. Like it's an instrument that we can use because we can make predictions about how these particles should behave based on what we know about physics. And we're comparing those predictions against measurements. So they're useful for us to explore new kinds of physics, but it's difficult to make some new technology out of it. Maybe there is a technology that uses muons that I haven't thought about, but
I can tell you about some.
Sure.
The at the Fukushima reactor, they're using muon scattering to probe where the reactor core bits have wound up.
Wow.
Because the cosmic ray muons come down and they scatter off the uranium and plutonium and all the stuff that's in the melted material, and they can track the scattered muons back to the material and figure out where it is. And then I'm a scientific instrument builder, and lately I've been building sensitive radiation detectors, and I just use the cosmic ray muons on my lab bench as calibrators.
Huh.
That's how I test my radiation detection equipment.
There's another thing which I should correct myself, Ivan, you're right. It's 2 microseconds, the lifetime of the muon. I got it wrong, I don't know why. 2 microseconds, you're right. But then there was a use of the muons for looking for hidden chambers in the pyramids of Giza.
That's where you're going, right?
That's where I was going.
Alvarez did that. So you're right. Cosmic muons coming down from the sky from pion decay created in cosmic ray showers. So they put the muon detectors in a known chamber low down in the pyramid of Giza, one of them, and they could see that they could see chambers. It's like X-raying the pyramids, and they showed we don't see any chambers that we didn't know about already. But this is they do have some applications like that. Yeah.
You can also get, I don't remember the details, but somehow you can turn your smartphone into a muon detector.
Ooh.
I don't remember if it's just a program that you load or if you have to get, you have to do something to the camera, I think. Maybe you cover up the camera so that it can't get any light. Pardon me, got something in my eye. You cover up the camera lens on your phone so it can't get any light. And then you activate this program, and if the sensor in your smartphone says, aha, I saw a bit of energy, it's likely that bit of energy is a muon, and obviously not a photon because you've covered up the screen. So I think that you can turn your smartphone into a muon detector.
So you
Not
use
many
television
per
to
millimeter.
see the microwave background. You just turn it to a non-channel, and
Old
much
televisions.
of the haze you saw
Static.
was actually not static. It was the cosmic microwaves coming through.
There's a signal from the ancient universe.
Oh,
How about that?
we're listening to the aliens.
I wanted to add one thing about, we were talking about, not knowing what 95% of the universe was. And I think this number gets thrown around in a misleading way sometimes, like, maybe it's 95% by volume or something, but not in terms of 95%. Like usually it's when people say, use it as an excuse, they're often using it as, hey, this thing happening under the streetlight may be wrong because we don't know 95% of what's out there. Well, we don't know 95% of what's way away from the streetlight, but under the streetlight, we know pretty well what's going on, right? So
Oh, yeah, the streetlight's a really good streetlight. It's just only illuminates 5% of the stuff.
It happens to be all the stuff that we care most about: chemistry, you know, ballistics, how rocks fall and how leaves fall and how leaves respond to photons from the sun and how stars work. All the stuff that has immediate existential impact on our lives is the stuff that we're also happen to be looking at under the streetlight.
And if we look at, again, we go back to how much does it weigh? What's the mass of the actual mass of the visible universe and our universe against the mass of everything else? I don't know that that's 95%. It doesn't, you know, dark energy has no weight.
Well, in terms of mass,
of course it does.
Mass, it's about 20% that we know.
MC squared,
Yeah.
yes, hypothetical, yeah.
So put aside dark energy because, you know, but
well, dark energy is energy, and it's you know, it's 75% of the mass energy of the universe. Mass and energy are the same thing. So yeah, we call it energy because of historical reasons, but mass and energy are the same thing. You know,
But
But there's that C squared thing that gets in the way. That's a big number.
Yeah. We work in units where we set C to 1. You know, it's easy.
about muons, some people got quite excited, unreasonably so, about muonic atoms and muon catalyzed fusion. Right? So you know, you can put you can slow down a negative muon and let it stop, and it go into an orbit around a nucleus and make a so-called muonic atom. It's the muon, being heavier than the electron, is very close to the nucleus. So some people thought, well, if we make molecules of deuterium, for example, a DD molecule, and put a muon in, it's going to pull the deuterium close enough to get fusion. And I do believe, I think, if I'm not mistaken, they did observe some fusion. I mean, but you know, it costs so much energy to make muons. It's completely, you know, it's completely out of the question as far as any energy source is concerned. But it's interesting atomic physics, if you like, to do that. And these muonic atoms enable you to measure the size of the nucleus out at larger distances because the muon is going close in. So muonic hydrogen, that's a subject for science research. It's got, but no practical application, because as you say, they decay quickly, 2 microseconds. Yeah.
So I have a question.
On the subject of using silicon image sensors, yes, silicon image sensors are sensitive to muons, and if you have very sensitive ones, you do see quite a few muons. I'm involved in the TESS planet finding mission, and actually we measured the depth of the silicon, of the active silicon in the cameras by looking at muons.
Great. Ivan, you had something?
Yeah, I was going to ask you guys what you think of these papers that keep coming up that say that dark matter or dark energy may just be a measurement error or may not be real at all. And I think my sense is the consensus is that they're probably real in some way. That, you know, dark matter seems to be clumpy, for example. But what do you guys think?
Okay, astrophysicist here. Dark matter has, of course, been around for as an object to be studied since the 1950s, when simply couldn't figure out galaxy rotation curves without it. And nothing we know about the dynamics of galaxies and of clusters of galaxies makes sense without dark matter. And then I was around in the 1980s when people were trying to make sense of large scale clustering and trying to figure out what the dark matter could be in order to explain the features that we see in superclusters of galaxies and even larger scales. And they're doing huge n-body simulations of large pieces of the universe, and they just couldn't make anything that looked very much like the real universe. And then I went to a colloquium and they gave one of these talks and they showed their n-body simulations and they showed, this case doesn't work and that case doesn't work and all that. And at the end, sort of embarrassingly, I should say, they said, but we throw in a little bit of Einstein's cosmological constant and look what happens. And they simulated a universe that looked like the real universe. And this was before everybody had heard about it, because then it was a few years later that got the type 1a supernovae calibrated real well, so we could look at what we thought was going to be deceleration of the Hubble expansion, and instead what we saw was acceleration. And that fit with what the n-body simulations had been saying. And then when there was WMAP, the cosmic background, microwave background radiation mission that mapped the cosmic microwave background, I remember going to a colloquium where a theorist presented a slide of what they expected for the spectrum of the fluctuations in the cosmic microwave background. And it was really quite detailed. And I thought, you guys are crazy. It's not going to be like that. And lo and behold, they were right. They got it just right. But they had to use dark matter, dark energy, the whole 9 yards to get it right. There is now finally a discrepancy that's showing up. The cosmic microwave background measurement of the Hubble parameter extrapolated to the present day is a little smaller than the best measurements in the current universe. And so that's a really big deal. But of course, this is great progress, because when I started as an astronomer, we didn't know what it was within a factor of 2, and now we're arguing over a 7% discrepancy. So we're getting a lot better.
Yeah, and that's fantastic and phenomenal. We didn't know when most of us were born, and I think all of us here in the panel, when all of us were born, dark matter and dark energy were barely recognized. There was the rotation curves, like you talk about, that came about from the work of Zwicky and Vera Rubin and some other astronomers. But in the past 50 years, there has been progress. We still don't know what it is, but we've really eliminated a lot of possible things. I remember
a lot of things it isn't.
Right. And one of my favorite is the idea of MOND, modified Newtonian dynamics. So for quite some time, for a couple of decades, maybe 3 decades, there is this notion that maybe we've got the theory of gravity wrong. Maybe there's no dark matter and dark energy. Maybe what it is that the pencil and paper that have been leaving these equations scattered around in libraries on Earth, maybe those scratchings that have emanated from human minds, maybe those equations are wrong. Nature's just doing what nature does. And instead of saying that our equations may be wrong, we've invented 75 or 95% more stuff in the universe just so that our equations won't be wrong. Well, I kind of bought into that early on, and then the bullet cluster happened.
The
bullet cluster.
So that's, I mean, the dark matter evidence is I think, as John says, I think very incontrovertible. Whether it's made of particles or not is a bit of a different issue. And it's even conceivable that it's not particulate or even lumpy matter, but some continuum. I mean, this goes against the grain of quantum field theory that says fields have quanta with them, like the electromagnetic field has got the photon and so on. But it's not, you know, inconceivable to me. But dark energy is in a whole different game because,
Yes.
and really, I think it's quite wrong. Dark energy got the Nobel Prize. Dark matter didn't get a Nobel Prize, even though it was much more soundly established than dark energy was. Vera Rubin, she should have got it, and we all think that too. Zwicky was the first on the game, but he actually got it wrong by a big factor, actually, didn't he? But he was doing how clusters of galaxies clump together. I mean, you know, dark energy. So it does seem that the more distant galaxies are moving away faster from us than you'd expect without something new, like a cosmological constant, whatever that is, you know. But so. You know, I wouldn't bet my life on dark energy, actually. I mean, there could be something wrong with those very distant galaxies. I don't know. But dark matter is established for what it's there. It's got gravity, but what it is
And why it's changing and why it was different in the early universe versus the universe we see today. You know, what John was saying.
We don't know. It's really not to explain this 7% discrepancy. It doesn't change very much. Let me point out that if you start from general relativity doesn't tell you anything about particles and fields. You have to paste in the rules for the particles and fields.
Right.
And the easiest field to paste in is dark energy.
Yeah, it's already there in the equation.
So if you're a physical minimum, yeah, well, Einstein put it in the equation because he was philosophically attached to a static universe, and it didn't actually work for that. But on the other hand, it remains the simplest field to stick in. It's one number. And every other field is more complicated than that. So, you know, if the totalitarian principle rules the universe, everything not forbidden is required. Perhaps from a sense of minimalism, at least, we should expect that the simplest field to put into a general relativity might actually exist.
John, following up on that, you're talking about it as a field. I like to talk about as a field, but all the fields we know have got quanta that go with them. And so you can ask, what are the properties of the quantum of the dark energy field, right? And that's the question I asked. And there's a paper you can find out if you look at on the web for dark energy tachyons. I've written about it because you know tachyons. By the way, they're not absolutely forbidden by relativity. Relativity says nothing that's got mass can travel faster than the speed of light, but tachyons have got imaginary component of the mass. They don't have a real component of the mass. And anyway, so that a tachyon gas would mutually repel each other. Now, a criticism of that is that if the tachyon gas is blowing itself apart, they're going to get farther and farther away from each other, and the repulsive force will die down, which actually could happen in the far future. On the other hand, you can create tachyons with zero energy. So you can create tachyons in pairs, actually, as the universe expands to keep the density constant. And it doesn't have to be perfectly constant. Maybe the dark energy field does have a time dependence, you know, on the time scale of billions of years. I don't know, anyway. But
so I want to, we just have a few minutes left. I want to wrap back around to the idea of the muon and how it's relevant to some of these discussions we've been having about dark energy and dark matter. Our current cosmological theory about the origin of the universe itself stipulates that at the beginning there was essentially just potential fields, right? As Mike alluded to in his comment just now, according to the best that we understand nature, the best way we understand nature, every fundamental particle is associated with a fundamental field. Right. There's an electron. Well, it's not really Noether's theorem, but it's quantum field theory. And so every an electron is associated with an electron field. The muon has a muon field. The photon has the electromagnetic field. So some of these fields you're familiar with already. And when the universe began expanding. It started from a spot that was not zero in size, but it was small. And from this small, dense nugget, the universe, essentially all of the particles and forces that we see kind of froze out of that. As the universe expanded and cooled, that potential energy got dumped into or converted into making the matter and dark matter, presumably, that we see around us today. The question is, the dark matter, how that came about from a potential field and what kinds of particles are entailed in the generation of dark matter is a complete mystery. And it may be, I emphasize that word, may be, that the experiments with muons that are happening this year open a little bit of a crack in our otherwise pretty tightly sealed model of the way particles and fields work, and provides a toehold for some kind of new particle and associated new field and potentially new interactions. And maybe this has something to do with dark matter. But this is all speculation. Dark matter, as Mike and John have very clearly said, dark matter is a well-proven idea by now, but nobody knows what it is, where it came from, how it relates to the early stages of the Big Bang. Was all dark matter created in the first few femtoseconds of the early universe, and then none's been generated since then because nothing has enough energy to generate those particles, et cetera, et cetera. So this might give us a toehold to answering some of the mysteries that are still outstanding about the fundamental physics of the universe.
Let me interject something, and that is that the disturbing thing about dark matter to some people is that it's matter and it has mass, and we can measure its mass and the effects of that, the gravitational effects of that mass. And that is supposedly something that shouldn't happen in physics. But the truth is, it took us 200 years to figure out what the sun was made of. Between the time that Newton figured out that the sun had mass and the time we figured out what the sun was made of, a couple of centuries elapsed. So this is actually not a new situation in physics at all.
Yeah.
But John, we have tens of thousands of physicists working on the problem, and Newton was almost by himself, right? So anyway.
Well, we had a lot of physicists work on the problem in those 200 years.
Yeah.
You know, one of the things you remind me of is that many of the ideas, Mike, you alluded to this earlier. I think, Ivan, you might have touched on this as well, that over the past 30 years, there have been innumerable ideas about what dark matter might be constituted of, what kinds of interactions, what kinds of particles, etc. And so far, every experiment to test one of these very clever, very elegant ideas, every single experiment has failed.
No. Experiments don't fail. They didn't find it because it wasn't
true.
there.
Right. Yeah, the experiment was successful. Thank you, Mike. That's an important clarification.
There were negative results.
Yeah, it was, the experiments were a resounding success at putting a nail in the coffin of some of these ideas.
So we've shown, for example, that supersymmetric particles, which may certainly exist, but they don't couple to normal matter particles and have a mass less than 2 TeV or something from the LHC. We've got limits on that, because we're searching, haven't found them. Maybe they're actually light and weakly interacting, and maybe it's we haven't explored the whole of parameter space, all the masses.
But we've ruled out all the easy stuff, certainly.
Yeah, the under the lamppost stuff, if you like. But,
all right. Well, thank you for joining us. Thank you for our viewers. Thank you for our panelists. It has been really
that was a wonderful explanation. Thank you.
Yeah, thanks, Mike and John and Ivan for talking to us about muons and both the practical uses and the theoretical implication for our understanding of nature. So we'll see you again in a couple of weeks. Abby will be leading the discussion in 2 weeks. I think she's going to be talking about sexuality in nature and the animal kingdom, and how some of our conceptions about gender and whatnot you know, just don't really hold once you start looking at the animal kingdom. So,
It's all-
all right. Thanks, everybody. Take
Bye.
care.
Bye.